Thanks for inviting me. This is my wife, Mirela. She's a genius, so that's why.
Or your wife.
So I appreciate the opportunity, and I'm excited that I got people that are interested in what I did 40 years ago. I mean, it's amazing. And, you know, it's said in America that the Danish people are the happiest people in the world. And I can understand why. We love being in Denmark, and it's a wonderful place. So I'm Mike Druke. I was employee number 17 at Rational, and I was the director of hardware. And I'll be talking about something I designed 40 years ago. So forgive my old memory. But here's evidence I'm not that old. Saturday, Mirela and I walked 20 kilometers around Copenhagen. 1,000 of those steps were, and there's proof. I mean, I took that with my camera at the top of that tower.
This is the most interesting place in all of Copenhagen. That's what I usually say. The top of that thing is the most interesting place in Copenhagen.
It really, I mean, I can't say I didn't rest a few times on the way up, but
there are 400 steps.
But here's, I made it, right?
You made it.
Yeah.
I swear.
And you managed to photograph the ball on the top. You must have held out your camera like this.
I had to. I was worried about dropping my camera because when you go up that spiral, it ends. It just ends.
Yes, I know. It ends.
I was expecting that. I thought there was a platform.
No.
No. So yesterday we went to Hamlet's Castle, and I want to establish that I am a nerd. Not just that I have a nerd pack, but that I'm always thinking nerdy things. So here's a quiz, a riddle. Who here knows what 0xd4 has to do with Hamlet? What's the connection between hexadecimal dog 4 and Hamlet? Anybody? Mirela?
Not to be.
Not to be. That's, it takes a mechanical engineer. It takes a mechanical engineer to get that, right?
You actually have 2B and then D4. And then
So I'm not going to waste a lot of time on who I am, but very briefly, I'm very proud that I'm a Vermonter. Vermont is the best state in the United States and the second smallest. You know, it only has, how many people in Copenhagen?
about 1.3 million.
Oh, there's 2 people in Copenhagen for every person in Vermont, right? So, but here's proof. I'm 3 years old and I'm picking potatoes with my sisters. And my dad, he just died last year at 98. And I would take him deer hunting every year. Here's it, 92. You know, he's got his gun and his cane. If he sees a deer, he drops the cane. But one of the things about Dad, and let me get this, is when they dropped me off at college, I was 16, and my mom cried all the way home. But my dad gave me this, and I've had this with me my entire career. And this says, "The secret of success is in this box." You know, so Dad gives me this, and I go, the secret of success is in this box. Wow. And let me tell you, I mean, I had this on my desk every single job. And my whole career, I've been working more than 50 years. And the Rational years were some of the hardest working, but most productive years. And we would work, and I'm not kidding, from 10 in the morning until 5 in the morning. And go, except for on Sundays. And then we'd go back, you know, get a little sleep, come back. We, you know, worked very, very hard there. So I found my passion for hardware at MIT. This is a picture of me and the first computer I ever designed. This reminds me of that machine you have, because these little boards here are exactly like that. 4 transistors, 8 resistors, a few capacitors, and it's maybe one flip-flop or 3 gates per board. And we just all push pin. Of course, we didn't have to worry about propagation delays. It was running at a megahertz. Well, twice as fast as that. But, and I was lucky enough. Right after my parents dropped me off and my mom cried all the way back to Vermont, I immediately lucked out and met Dave Bernstein. For some reason, we both liked pool. We met at playing pool, and we decided to be roommates. And Dave and I have been close. Our car right now is parked in his yard. He lives in Boston, and we're flying back to Boston. So Dave and I, Dave was the vice president of engineering at Rational. He and I got the passion for digital systems early, and when I look at that picture and I think about what I'm doing now, or just you showing me that stuff you showed me with that 1,000 CPS printer. I mean, I'm as happy doing this stuff now. So it's very important to find your passion in life. When I try to mentor young kids, you got to find out what you're good about and what's not work, which just you're good at and you're happy doing. And designing that. No, Dave and I, so our junior year, our professor that was here got us a job at Data General. So I had a choice to go back to Vermont, live with my mother, and work in a toilet paper factory, or stay in Cambridge, live with my girlfriend, and design computers. Okay. So Dave and I was 19, and we designed the Nova 2. And I see you have a Nova 2 here. That was designed by a couple kids. That's why when you ask, if I ever work for a big company, tell me a big company that would let 2 19-year-olds design a computer, right? Data General had that environment, though. You know, it's whatever you can do, or whoever can do it best, do it, you know. And so I joined Rational as employee 17. Dave was 16. He got there a month before me. And he was the VP of engineering. So so what happened is we graduated from MIT. He went immediately to Data General and designed the Nova 3, where I stayed at MIT and worked with Marvin Minsky on AI. And ever since, he's been my boss. Now, that doesn't mean don't go to graduate school, but it means, but that's what's happened. He stayed there. He was my boss at Data General. I mean, he was my boss at Data General and my boss at Rational. So enough of the personal stuff. So now about Rational. So we were formed in 1981 by 3 Air Force Academy grads. These guys were, they saw the potential for Ada. They saw the horrible type of software architecture and just spaghetti code that existed out there. And especially Grady Booch. If any of you know software, you know who Grady Booch is. And Mike Devlin was the software guy, and Paul Levy was a business guy. So the Air Force Academy sent them both to Stanford, and that's how they came out there. Grady stayed in Colorado Springs and worked at the Air Force Academy. They had to do their time in the Air Force, but they were lucky. But they worked at the Blue Cube, Mike and Paul, which was this top secret Air Force base in Sunnyvale, had to do with satellite tracking. And they would often come to work in their captain's uniforms, and you know, it was good that they could coexist. The first financing was Arthur Rock, and he was the chairman of the board, but he was the guy that financed Apple and Intel. So we felt very special that we had that type of, because he really was convinced that we were onto something to revolutionize software. And he backed us with money. So we never really had money problems in the first few years at all. And one time he came when we got the first prototype, and I'm showing him the machine. He goes, "Well, where's the compiler?" I'm a hardware guy. I mean, what do you mean, where's the compiler? So I pointed to the disk, right? I mean, it's just bits, Arthur. but one of the good things, we had a rule, nobody left on Thursday. So every Thursday we would have a barbecue for the whole company, and then we would stay and we would have a seminar. So somebody would present what they're working on. And that was great for the culture because, I mean, everybody knew what everybody else was working on. And you can't believe how many hardware problems were solved by some software guy that I was explaining what I was doing. Or even once in a while, I would solve a software problem that a software guy would, that type of collaborative environment was, I mean, Rational was a special company, and especially in those days. And these things usually lasted past midnight. That's why this nobody leaves on Thursday rule. And then on Fridays, most of us would go to Grand China and have Chinese food and eat, and that would kind of end. But we usually work Saturdays as well. And we used to have company picnics. And the first one I remember well because William Perry, he's still alive, he's about 95. He's the former DOD secretary, Department of Defense. So he was and he's considered the father of the cruise missile. Now, I'm a pacifist. I'm not so much into military and everything, and there was a lot of connection, though, with Ada and military in those days, and I tolerated it. And this guy was a reasonable, I mean, his philosophy is the cruise missile was going to save lives and support peace. So we had very, very influential people. And I'm talking about a company with like 25 nerds, right? And that's what we were in the early days.
Before you
Yeah.
can I ask a question?
Yeah.
This question here, where is the compiler? What kind of answer did he expect to get?
Well, see, all he knew is one of our biggest milestones was we were going to sell an Ada compiler to Rome.
Yes, okay.
And that was going to bring money. That's the first time we brought. See, he's money, right?
Yeah, right.
So he's saying, we got to develop this Ada compiler for Rome. And so when I'm showing him all my hardware and where's the compiler?
Okay, so he wasn't technically...
He's not technical at all.
All right.
No, Arthur Rock is just a money man.
Yeah, all right. Okay.
And so he
wanted to see
there is some. So, when we started out, we made a few very, very important design decisions early. And the first one was that we would use CAD. Now, I'm talking 1982, early 1982. There was no CAD. Luckily, when I flew out in late 81 to interview there, on the airplane from Boston to San Francisco was a guy I worked with at Data General that had just started. He was the CEO of Daisy. And so Daisy was a company that was a startup, and we were their first customer. I arranged for Mike Devlin, one of the founders, and that was part of my interview. Here, Mike, let's go buy some daisies. Because if you want me to design all this hardware with like five guys, that's all I had, or 4 hardware guys and a software guy, I need CAD. And CAD's the way to go. So that was a very important one. And we spent $150,000 to buy. They were $75,000 each, which was a lot. That impressed me, and I was sold anyways, but I tried to play a little hard to get, But anyways, the fact that they were willing to invest, because that's been the key to my career too, is a small group of smart people with the right tools can do what 100 other ones. Our CFO was at a party, in the old days, and rubbing shoulders with, chief financial officers and how we built this big 128-bit machine and everything. And they ask him, how many hardware guys do you have? He goes, 4. And they couldn't believe him. But then he said, well, Mike's the director of hardware, and he designed some too. So we really had 5, right? But anyways, the next big decision we made was to go right to PCB. I saw one of your wire wrap. I don't know how many of you guys have ever struggled with wire wrap, right? You have, yeah. You know how it always breaks out right at the, and you can, some you can't even see. It's just, you know, it looks perfect, yet it's discontinuous. It was horrible. I had already put in my dues with YRAP. I said, if we write a simulator, we can go right to printed circuit board, and it'll be quicker. We'll get a product earlier. People, oh, we're going to waste all this money. We have 5 boards. All 5 of them work first time. Mostly based on the simulator, but also just good, solid layout. And the fact that, you know, in the old days, you used to have to red line. One guy was with the net list with layout, and the other guy is at the schematic and red line this. You know, I mean, none of that. And so we were able to go right to PCB, and that was important. And, you know, we had a simulator, but we were rational, right? We always said, software are us. I don't know, there's a thing in America, Toys R Us or whatever, you know, right? And it was, of course, written in Ada. And that was one of the great things about Rational, was that we were our own best customer, right? I mean, a lot of companies, they have a test group that tests the product and tries to figure out different user scenarios. No, at Rational, we had a tool to write Ada, and what did we do? Write a lot of Ada, you know, so we were our own best test. So the next thing was that we would upfront build in powerful diagnostics. We wouldn't treat test as an afterthought. Test was the first thought. And what we did is we found the Intel 8051, which is a very primitive little microcontroller. It had 128 bytes of RAM, but it was had a lot of ROM, so you could build descriptors of data, of registers and things like that in ROM. And so we had what we called a diagnostic archipelago. You know, the word archipelago is just, you know, many islands. You're like Indonesia. Indonesia is an archipelago. So we called it because every board had the diagnostic island, had an 8052. And we also decided, when we looked at layout and how to do things, that we would have a backplane and a foreplane. And what that meant, we don't have one of the boards, but it was, you know, a big board. And if you think about layout, if everything goes to the backplane, you'd have signals that would have to come up and around again. But the way the flow of the signals worked, it would go between the backplane and the foreplane. So if you look at these boards, I mean, we laid out these pretty complicated boards with 4-layer boards. And remember, 2 of the layers, power and ground, you know, so it's just one signal pair. And so that was very important. And it turned out it was useful for hardware debugging, and then useful for manufacturing, and then useful for service. And I'd skip back to that. But yeah, anyways, the layout was a lot easier, and we did it with 4-layer boards because we put the back. Now, the 4 planes proved to be a little bit of a problem. Somehow they were, because they had to be 0 insertion force. So there was those little levers, but the field guys learned that you just twist the lever a couple of times and then it would make contact. But there was also a good diagnostic. If there was any discontinuity in the 4-plane, we'd find it out like that. And the final thing was, you know, we would go with our strengths. Our strengths was designing an Ada machine. It wasn't I/O. And that's why I don't know so much about the I/O. I stay away from I/O. Anyways, so what we ended up with, we used to call it the world's most expensive unibus peripheral, because there was actually 4. The first machine, the Series 100, was a quad processor. It was a huge monster. And it had 4 PDP-11s built in to control all the I/O. I mean, it was amazing. And so that was part of it, is let DEC worry about I/O. And we could buy off-the-shelf DEC tape controllers, COM controllers, disk controllers, things like that.
So why digital? Why not data general?
What?
Why digital? Why not data general?
Digital had better I/O.
Okay.
Well, you saw the Nova 2,
Yeah.
and I mean that I/O was ugly.
You knew
But-
that one.
But also off-the-shelf I/O controllers. So in those days, you couldn't go off and buy a COM controller. You had to buy it from Data General.
Okay.
Whereas you could buy an off-the-shelf tape controller, disk controller, COM controller. Those are the three main ones. Ethernet was like a dream in those. I mean, we didn't even have that.
Who made your ADA compiler?
Who made the Ada compiler?
Yeah.
Harold.
Harold.
We had a one-man compiler guy.
Okay.
You know, that was the first job, was actually to make an Ada compiler
Okay.
and sell it to Rome.
Yeah.
So we sold it to Rome, who then they made a military version of the Data General machine.
Okay.
So ROHM is the name of it, or ROLM, I think.
Yeah.
And so Harold, he was just an amazing guy. He was one of these kind of, out there software guys. I mean, like, wasn't really part of the universe, Yeah, I don't know. Harold was an interesting guy. I like him. Harold Larson was his name. He was a smart guy. Well, obviously. But he, a one-man compiler guy. And he did what 30 people at DEC were trying to do.
Exactly.
And Harold did it in half the time that they didn't do it, right? They never. So, now, diagnostic was the important, one of the things I taught. And so, one of the specs I made, requirements for the boards, is every board would drive and receive its external pins. So even if I was driving a pin to Paul Henning's board, not only would he have to also drive it himself and receive it, but I would have to receive it. That way, if the board was standalone and there was a problem with connectivity to the backplane, we could detect it. So we wanted to be able to detect 100% coverage of every board standalone. So also that all registers were either scannable or you could do an operation to make it load into a scannable register. This was before what they call boundary scan and things like that nowadays. We came up with it back then. And so then we made a test board with a zero insertion force. That's what I mean by ZIF. Zero insertion force connector. I see you have one there. It's, you can plug the board in and it is powered. You have a UART line to the 8051 and you could run 100% coverage diagnostics. And so that turned out to be absolutely useful in bringing up the hardware. It turned out to be very useful. I mean, that's how manufacturing tested the boards. And these are the days when people were spending $50,000 for a bed and nails tester, to test boards. And they would spend not only, that was just for the jig. And then they would have the people program it. Cost you another $50,000. I mean, test fixtures were costing $100,000 to manufacture in those days. Ours cost, I think, $1,500, right, just to make these jigs, because it was built in. And Chris Jakes is a genius. I mean, if Chris Jakes were alive today, all your problems would be over. Because his memory was, it's very, I'm sure he would know the answer to a lot of things. And he was a software genius. So one of the things I've always done, people say, why are you still a director? Right? Because I was a director of hardware at Rational in 81. And then I was director at Intuitive Surgical in 91. And then, I was director, and I say I want on my tombstone he never was a VP. Because I want to do real work, right? But anyways, every group I've had, I said, I want a good software person in the hardware group. Because tools are important. And it's not just tools you can buy. 90% of the useful tools are the ones you build yourself. So, And also diagnostics. We didn't have a diagnostic group. I just said to each hardware guy, and I did it too, you're going to write your own diagnostics. Now, how better can the hardware guy communicate with the diagnostic guy? Excuse me, well, I'm not being sexist. There were no, I'll say guy, okay?
That's all right.
If the hardware guy was the diagnostic guy, the communication was quite good, you know. So, and we all, and in those days, there were these like graphs that show how many 1,000 lines of code the average software guy writes. And 50,000 was like a really super good guy. But one of the things that's very interesting is you see that graph and then it goes down. And why does it go down? Because the best software people write less code. It's just more elegant, right? You know. But we all wrote, and you asked why it was Pascal. It was like, it was, at first, it was for the, 6800 or for the PDP-11. And the first diagnostics ran on the PDP-11. There were no Ada compiler. DEC had 30 guys trying to do what Harold did in one, or Howard did in one, and never had it. There wasn't an Ada compiler for a DEC machine. And I'm glad there wasn't, because then we would have, when we switched to the 68,000, we would have had to have a problem. So one of the things about it is there was a signal, it was called diag freeze, and any board could pull it down, and that would stop the clock. I mean, I designed the whole clock system to be like stop on a dime. You can stop in the same cycle that the error was detected. And that means the data is preserved. And then you could scan it out. So we would create what we called a tombstone file, and then we wrote what we call post-mortem diagnostics, and it would isolate to the fru. And it turns out the first machine that failed was in Sunnyvale at Moffett Air Force Base, and they were testing it so it wasn't in a secure area so that we had remote diagnostics. And our guy showed up with a board in hand just as they were figuring out that the machine crashed, and he replaced it. So it was good feedback of this remote diagnostics. And now, in terms of the board partitioning and the hardware team, again, I was the hardware director. I'm just, we'll get Grady Bucci here sometime or somebody to talk about software. But and I designed the memory board. I wanted to blaze the trail for DAISY to show the standards of how we design, how we name signals, and how we draw schematics, but also how we lay them out. So the first design was 8 megabytes because it was, huge amount of RAM in those days, 256K bits per chip. But the first thing I decided was that I didn't want to build in another whole section that most computers did. If you look at any computers, the VAX, the MV6000, which are like coincident with this machine, and all the IBM machines, they would have what they called an address translation unit. And it would take the logical address in and go up in the page table lookup, and then create the physical address, and then you would address the memory. No. Generally at Rational, one of our first questions when we had to design something was, how does everybody else do it? And you'd get the answer, you say, okay, that's not how we're going to do it. Right? So, so what I was enamored with, I was designing caches at Data General and was designing 4-set associative in those days. And what I came up with is a design where, so when you have dynamic RAMs, you have what's called row address strobe, column address strobe, because 256K bits needed 18 bits. They didn't want to have 18 pins, so they time multiplex the address pins. And also the way the internals work, they had rows and columns. So the row address was given first, and then the column address. So we would give the row address from just a hash function. It was 5 nanoseconds delay through an exclusive OR gate. So we would take the logical address, hash it down to a page, and then that would be the row address. And now in parallel with the row address axis, and in time for the column address stub, I would quadruple pump 4 duplicated tag stores to get 16 set associative. And if you look at graphs of set associativity numbers, it gets asymptotic with infinite or fully associative at around 8. In fact, nowadays you don't see, even in today's, they have level 1 caches, level 2 caches, level 3 caches. You don't see something that's even 8 set associative. Sometimes you might, but I haven't studied that in a while. I've been out of computer design for quite a while. But anyways, this was 16 set associative, so it was nearly, it was just, you just give it the logical address and it'll go, oh, here's your 128 bits. It was 128 bits wide. And so there was no notion of a physical address. It kind of was deep down in the diagnostics. You say, I want to get at this RAM. You know, you could do it, but. And so it was 128 bits. And it was just recently, you know, that there were 128 machines out, right? I mean, this machine, the rational machine, was a 128-bit machine in the 80s. By the way, the PC board fab house took my Gerber after laying it out, and they go, "Brr." No, you've got 0.2 vias for every component pad. Our software says you have to have at least 1 via for every component pad. And I said, why? I mean, you know, you can lay the board out where if you do and you scramble your data, and we did it right. And that's where Chris came in. Chris could take the schematics in the database of DAISY and then just figure out how to lay it out and redo the schematics, and it would just lay out as straight shots, as we call it. And there literally was 5 component pads for every via on that board. So they finally, I convinced them, build it. I'll sign a disclosure. You know, it's fine. There's not that many vias. And that's an example of what we eventually call the Gestalt design methodology. Gestalt meaning the psychiatry of the whole, where, you know, Gestalt came up with a thing that the whole is more than the sum of the parts. So, but a design, you have to think about the physical design, the logical design, the manufacturability, the testability, the supportability, maintainability. If you think about it all at once, you know, you come up with a better design. And that was an example of the Gestalt design. The val type and FIUs. So Steve Schroeder did, I put the initials down because later we'll get into one of the things I did on every backplane is put the initials of everybody in the company on the backplane to really show everybody had a part of it. And so Steve Schroeder, he lives in Portland now. He came to our house with Mary I'm going to contact him. He might remember. But I think he left before the 400. I'm a little unclear exactly when people left. He did both the val and the type. And the reason for that is they're pretty identical in the sense that it's one big 64-bit ALU. The type board has extra stuff. So for instance, in the rational machine, you can say, I declare an integer that's between -7 and +66. And the compiler would immediately say, that can fit in 7 bits, and here's the lower bound, here's the upper bound, and the type board would check that in on the fly, whereas on a traditional machine, the compiler would have to generate extra code. Okay, this is this type, and, you know, is it greater than the lower bound, less than the upper bound, all that in series, whereas the type board would do it all in parallel, which is good. Now, Steve, this board became known as a monument to MSI, which is basically, MSI means medium scale integration. So that means, you got the list of parts, right? They're all like quad this, octal this, right? I mean, it's just, and they're all mostly 20 pin dual inline, 10th inch space, easy to solder parts. And that's really what the Rational Machine was. And, but that's all you really had in those days. Steve was actually a high school friend of Mike Devlin, and he was the first hire. Grady, Mike, and Paul said, okay, we're going to need a hardware guy, because they decided really up front we're going to need to build our own hardware. And they did. Next was Mark Frappier that did the FIU. So I would give him 128 bits wide from the memory board. And he had these, how many multiplexers were on that board? But because in the olden days, you didn't have these chips that did, what they call barrel shifters. It was all done with multiplexers. And
we should probably say at this point that the rational computer doesn't work on bytes. It works on bits.
right,
So your integer might be 7 bits or 13 bits.
yeah.
And it can be anywhere in the word.
Right, yeah. We had a bit addressable logical, you had a logical address which was addressing the bit. And then part of the type declaration was how many bits. If it was more than 64 wide, I forgot what we did. Then the compiler had to chop it up. But also the FIU, though, would deal with fields. So you could say, I want a 2-bit field. And if you're really unlucky, it's the last bit in this 128 and the first bit in the next 128. It would handle that automatically and go ask me. And my board was smart enough to say it's the next column. Now, it's possible that you're really unlucky and you're crossing a page boundary, and then you have to a 2-bit entity could cross a page boundary. Theoretically. And when that happened, it still didn't involve any type of interrupt. It just meant that I had to go rehash and do another RAS, row address scope. And Mark worked with me at Data General. And so he was the first occupant of the Massachusetts Halfway House. Now, what was the Massachusetts Halfway House? One of the things they did to get me to come out was they said, okay, we'll buy you a house with a pool in Sunnyvale. I said, okay. Now, I was already sold on Rational, but it pays to play hard to get, right? But one of the things was we're going to hire a lot of people from outside of California. So one of the things about this Rational home that have is you got to put people up to transition. So most of them were Data General people that I hired or Dave hired, that we have what we call the Rational Mafia there, or the Data General Mafia. And Mark and Nina, his wife, were the first occupants of the Massachusetts Halfway House. The other thing was Grady Booch stayed off and worked at the Air Force Academy in Colorado Springs. So anytime Grady Booch came to Rational, to San Francisco, to Silicon Valley, I was supposed to let him stay at my house, which it wasn't a burden. I love to have Grady's. I learned so much from Grady, it's unbelievable. He's a sharp guy. So that's what I mean by the Massachusetts Halfway House. 1509, Bellardo, Sunnyvale. Then we have the sequencer sys and IOA. So Ed Pollack did the sequencer. And again, we're getting into areas that, it's not quite I/O, but I just let Ed handle that. And it had a writable control store. And it was basically, it just, sent fields out to everybody else to control all the ALUs and bus transfers and all that. It was somewhat uninteresting. Don't tell Ed that. Ed, a lot of people actually that worked for me in the early days are VPs, right? He turned out to be a VP at Sony, and he was very successful after Rational. And so he did that. Jim Wilson did the sys board. Now the sys doesn't exist on your machine because that was the board that handled the multiprocessing. Because the first R1000 was a multiprocessor. And it had an arbiter. So the address space, the logical address space was common among all four, and it would arbitrate and, do what's called cache coherence. The concept of cache coherence says that if I've got a cache over here and a cache over here, if I write, it better be reflected over in this other cache, because you're all reflecting the same universal memory. And Jim is a pretty bright guy. He lives in, he's retired, he lives in Arizona now, and I have contact with him. I'm going to ask him, but I think he left early because we punted the sys. So we'll find that out. Now, Dave Bernstein did the I/O adapter. So that only existed in the R1000 Series 100 because that was the board that interfaced to the PDP-11. But Dave did an amazing job because he was the vice president of engineering. So he had other Unreal work. Now, all managers at Rational did real work, meaning we managed by examples and we did design. We considered like sales and marketing, stuff like that as like a necessary evil, but they didn't do real work. I mean, we did the real work. We were the engineers. We were the nerds, right? So, anyways, so Dave not only was hiring up a team, and he was VP of engineering, so he was more important than hardware. And I used to admit it. We 5 hardware guys were. The software guys thought of us like we thought of the marketing guys as a necessary evil, right? But he managed all the software, which is really what Data General. What Rational was about. If you look at the different things like source control and just semantic driven editors and the old days, the things you get now in the Eclipse environment or other programming environment where you say, show me where this variable is declared, and you just press a button and now you're over at the source where this variable was declared. So that was Dave. Now the 6th person in the group was Chris Jakes, he worked for me at Data General on the Micro Eclipse. So, the first thing I did as I jumped to be a director of the next company was hire Chris, right? So the first thing I did at Rational was hire Chris. The first thing I did at Intuitive Surgical, hire Chris, right? He was one of the smartest guys I've ever worked with. And that's saying a lot because of these, we're talking about Grady Booch and Dave Bernstein and people like that. So he did XMON and the 8051 interpreter plus the DAISY tools. And like I say, every hardware group needs a software person. You really want to have tools to make your job easier. In general, we're lazy. I don't like doing, and in fact, I'm very bad at tedious tasks. I don't do tedious tasks well. Computers do tedious tasks well, but you need a really good software guy to understand your requirements and then make a tool that does it. So that was Chris. So then we get into, more of the history of the machines, So the Series 100 we did in 1983. We shipped the first one to Lockheed Martin, although Dave Bernstein told me the other day that was to Rome. I don't know. We'll have to get our memories lined up. We still know how to get a hold of Paul and Mike. Paul lives in Hawaii on Oahu, and Mike, I don't know where he is, but people know how to talk to him. But it was a massive machine. I still got just the I/O cabinet in my garage I use as a tool chest. And of course it's got disk slides. So I can pull out a drawer the whole way and look down into it because it's really a disk. But it was huge. And Mike was a big guy. He's bigger than me. And part of our UL safety testing was you have to be able to tip it 20 degrees and it should right itself. And it took everything that Mike and I could do to tip it. And I remember Bob Walton, the software or the manufacturing guy, with a protractor going, okay, you're at 18 degrees, 18, you have to go to 20. Oh, okay, we're at 20. Now jump. And sure enough, the thing came back, and it would have killed us if it would have tipped over. It was a huge machine. It's amazing we built that. And it cost $1 million. I mean, but Lockheed paid for it, government money. But anyways, so we got a lot of feedback that we don't want to do multiprocessing. So we punted the multiprocessing and the PB11s. And this was a critical thing. And I didn't even appreciate until we parked our car at Dave's house in Massachusetts because we came from our home in Vermont to fly out here. And so I talked a little about it here. And he told me about the amount of effort he had to do to convince DEC to license the Unibus to us. Okay, because we weren't about to design our own tape controller, our own disc controller, or comm controller. Why do that? That's I/O, I mean, somebody else does that better than us. And we already had drivers for those Unibus peripherals. So Dave managed to, I forgot who it was, somebody who was a past DG person, was actually at DEC at the time, that Jeff Kalb was the guy's name. Jeff Kalb was the guy that headed Data General Semiconductors. And he ended up switching over to DEC after Data General kind of went down. And he convinced Jeff Kalb to sign off on us having a Unibus patent, which was very good. And I don't know how Dave sold it, but Dave's a good salesman. And so we could keep the Unibus, but design a Motorola 68,000. Did I say 6800? That's either a typo or, it used to be a 6800, right? And we hired Wayne. Wayne was another resident of the Massachusetts Halfway House because we knew him from Data General. And we hired a guy, Ken Barton, from Tandem, who is a really good mechanical engineer, who did, the redesign of it, which was much more respectable. But it was still big because it had a big old hunkin' tape drives and those washing machine discs almost, in those days, those discs were pretty big. But again, that's I/O. I don't do I/O. I do hardware. But, so the next, we got into, again, this is I/O, which is, it just kept getting better and smaller. So this, we called it a skin job, but if you see a 300, it's a lot smaller, but not as small as a 400, but it didn't have a real tall cabinet with tape drives and things like that. It had, modern, and I think the disc drives were, they just kept getting smaller. I forgot exactly what the form. Not only, of course, everybody knows Moore's law, right? I mean, not only got smaller, it got higher capacity at the same time, a win-win. And the 400 is the one that you have here. And that was the ultimate one. There we finally said, okay, memory chips are now, 4 times bigger. Design a 32 meg. So I designed that. Now, it wasn't a huge hit for some of the software guys because it then only had 8 set associative. Oh, that's how it was. I was trying to think how I did 16 set associative, but it was 4 sets per board, and each board, there was 4 boards. So here it was only 8 set associative, which luckily by then the kernel guys had figured out how the code got allocated and could flatten it out so that, the kernel would not take any more than 2 sets,
So why does the 400 only have 2 memory boards?
We just wanted to make it smaller. Well, I mean, who ever needed more than 64 megabytes? I mean, Come on!
I think there was a guy called Bill who said he wanted 640.
It was like, I remember the early days of Data General when, you know, we were talking about the MV6000, or, you know, I worked on the Solar Machine predecessors, right? We wanted not 16. Now, the one that they first did was just way out there. You know, it was almost as complicated as Rational. Then the next one was Ego, which was a really reasonable 32-bit architecture. But it wasn't compatible with, it was compiler compatible, but not assembler compatible with existing code. And so the powers that be at Data General canceled Ego and did that MV8000. That's when most of us quit. They said, don't quit, form a microprocessor group, and that's when I did the micro Eclipse. But I remember back then, we were a 32-bit machine. Wow, 32 bits of address space. I mean, we're talking about 16 bits of address space in the old mini computer. Wow, and Data General was smart, and it was 16 bits. So that gives you 128 kilobytes. And that was more than enough. But then, wow, 32-bit address space, 4 gigabytes of memory. That's just like more than anybody needed. So, I mean, here, we're still in that kind of mindset back in 1990. I mean, 64 megabytes, that's more memory than you're ever going to need, right? So it was more the issue of only 8 sets associative that was the problem. Plus, you saw that little exabyte tape. Those little exabytes would, that's the first time I learned the term exa. Peta, exa. And then, 2 to the 24th wasn't named. You know what they named it? Hella. Really. So hellabyte, true, look it up. A hellabyte is beyond yada. There's yadabyte, and now there's hellabyte. Because they just keep having, I don't know, I mean, I think that's 2 to the 27th, right, or something. I got to go through it. Exa is, peta is 2 to the 12th. 2 to the 15th is exa, and then 2 to the 8th, take that offline. Anyhow, that's the series, okay? And
So at no point in this do you actually make the CPU run faster.
what's that?
You didn't try to make the CPU run faster?
No, because that would be redesigning the whole thing. Plus, it was running at 5 megahertz. I mean, gosh,
No, but I mean-
how much faster can you go?
No, but I mean, by 1990 you would have access to ALS technology chips and stuff like that.
Yeah, we actually did bring some ALS in, but you saw how many chips are there, right?
Yeah.
So think how many independent paths had to work in 200 nanoseconds, I thought about it. I'd like it. Well, we tried a design with 2901s.
Yeah.
So you could get a 2901, you could theoretically run at, 10 megahertz and read it, but it was just too much design. There's already a lot of investment in manufacturing and everything. And that machine runs the same speed as the Series 100 back in 83. Now, you got to forgive me. You let me take that picture without cleaning it.
Yeah.
Usually I take. I dug this out of our basement, and I actually do have an R1000 backplane just to show. And these are arc welder. These independently were powered, right? 200 amp power supplies each. You've seen those cables coming, they're arc welder. Once I was debugging and I shorted out power and ground, and immediately my brass rat, this is an MIT school ring, my brass rat was red hot, and I'm going, crap. Luckily Chris Jakes was there, and he slaps my hand, and 2 red hot pins, not this one, because the one that is missing 2 pins, were welded to my rat. We learned real quick to not wear rings when we're poking around, you know, the back plane when that's powered, because 200 amps. I mean, the whole sum of everything was 400 amps per processor, but you know, if you shorted 2 pins, it would give you the it would melt things because it was distributed. I mean, if you look real careful, you can see G, 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 G. Those are where there's grounds. We use that because we would put logic analyzers on there. This dust is courtesy of Half Moon Bay. That was added after the design. But, and then there's 6 here. That's because there were 4 I/O controllers. See, so this is Dave's I/O controller board.
So each of those goes to a PDP-11?
Each one of these had a unibus connector in the back.
Right.
It did not have a 4-plane. See, so there was a 4-plane here
Yeah.
on these boards and on each one of these, but these 4 just had, it was like we said, this was the world's most expensive unibus peripheral, right? Because it's just plugged into unibus. And it's hard to see on that one, but one of the things I did was we were always very proud of it. We were proud of everybody, even the marketing and the sales and the necessary evil people. So we would put everybody's name on the backplane, including Ada. So I would always put Ada first because she was the first. But this is everybody. I don't even know where MBD. I must have put myself there.
It looks like you sorted them by last name.
It's sorted by last name, so I think I might have chopped that off. I'm probably down here then. Anyways, we have everybody's. It's amazing. I chopped that off. That's too bad. Remind me to take another picture of that when we're back. But this shows that we replaced the SysBus with the IOC. Even at
So
the,
this is a 200?
this is the Series 300.
Oh, fair.
So it's 1986.
Right.
That's how we could tell. And so this tells us how many people were in the company. So it's 4, 8, 9, 10, 11. I think there's some list, 1, 2, 3, 4, 5, 6, 7, 8. It's about 100 people. But some of them, somewhere here, at some point somebody made me put Rock in there for Arthur Rock. I don't think I did it this time.
That's
all
the way to
Did anybody see? Yeah, there's Rock. So he's not an employee. He's the chairman of the board, the money guy that asked where's the compiler. But
You also
all
have
of-
Diane.
What's that?
And
You also
Wendy
have Diane.
and Laura.
That's not that. That was. We didn't have a lot of women,
Oh,
but
okay.
there was this hot software woman,
Oh, I
Diana.
thought
That
it
was
was
her.
the Ada semantic form.
Not Diana.
Ah.
No, Diana was the intermediate.
Ah, okay,
But
okay.
see, GGD, that's Gary Davidian.
Yeah.
We need to find him.
Yeah.
MTBD is Mike Devlin. And then we did the 400, or the 300. So that was the 200.
Yeah, it must have been the 200. Yeah.
Right, this is the 300. Now, let's see here. So I still put Arthur Rock in there. Now, here's how I dated that, because Dave and I couldn't remember the 400. And I know that my daughter Laurel was born in 1989, and there's no Laurel there. So the first machine I put Laurel on was the 400. But I got to be on this backplane. What the hell is going on? There, I know I was there the whole time. That's me. Dave Bernstein is DHB, whatever. I don't know if we put Rock. We put Rock on that one. And Barbie was, these are real people. Diane, Barbie, that. Wendy was another woman programmer. But so I had room there on that to put them all. Then we got into the 400, which you have, and then we have like 200 people. And you can't even see that totally here. But whoop, that doesn't make it bigger, that scrolls. I don't know how to make it bigger. But Tom Knight, the layout guy, what we did is we found a bunch of instances where there were 2-letter initials, so we could fit 3. You see there, we could fit 3. So we fit, and they were upset because we couldn't fit it. But you see, there's Laurel. That's my firstborn. So she shouldn't really be on there. But this helps date it. So I know that this is post 1989 because Laurel was born in 1989. And of course, Ada always was on top. I think I might have lost Rock in order to fit it. Rock was more important to me, less important to me than Laurel. So, yeah, I don't see Rock there anymore. And I think he kind of drifted away from us after, this is 89. And you guys know what those look like. So that's basically it that I could prepare. And thanks for the opportunity. Do you guys have any questions?
Could you talk a little bit about the Nova 2?
What's that?
Could you talk a little bit about the Nova 2?
Sure. So I already told you the story about my horrible choice and dilemma, and I decided to stay in Cambridge and live with my girlfriend and decided. So we get there, and we met Larry Seligman, who designed the Nova 1200, and he saw that Dave and I really were enthusiastic, really were sharp, knew what we were doing, and he said, "Look, I bet using this 74-172, which was a new chip out of TI, which was a quadruport RAM." So, because that was a big thing. I mean, you have 4 accumulators, you got all the data paths to multiplex them into an ALU. Here it was all your accumulators on one chip, and it was quadruport, which you needed because you only needed 3 ports, really. You needed 2 read ports and 1 write port. But actually, the second write port turned out to be a nice thing to have, too, because what Data General had was this notion of, in the instruction set, that you could shift the output. You couldn't, it wasn't a barrel shifter, but it was actually left, right, or swap. So you could also swap the bytes. So I think we did a swap the bytes with the other port. And so you saved a multiplexer. But, so Larry said, based on this, he had said, look, I did the 1200. It took, 1.2 microsecond. So it was like, 800 and something kilohertz machine. But I think you guys can design a machine. The earlier machine was an 800, which actually was a 1.25 megahertz machine that was on 2 boards. But both the 1200 and 800 were core memory based. So they were really, the architecture was ugly, and the control structure of the processors was, intertwined with inhibit wires and sense wires on the core memory, So Dave and I said, no, we're going to design a machine with a memory bus, because someday there's going to be semiconductor memory. If you really are confident, you read, I've heard that they have 64-bit RAMs now. It's only going to get better. This was before Gordon Moore came up with that, but you could see it in those days, right? Things are just getting better. So Dave and I sat down, designed, a data path with the 74-172s, all feeding. They had 74-181s, which are ALUs. And then you had to use a 182, which is carry look ahead. And we had this basic data path that looked like it would fit on one board. And we did the math. We said, we can do this in 600 nanoseconds, Gosh, 1.6 megahertz, the fastest machine known to man. And it's on one board. And, what more do you want? So the biggest problem was control. And so Dave and I had a bake-off because he was enamored with traditional microprogramming. And I said, I love microprogramming. I think it's a wonderful concept, but we got to get this on one board. And we can't spend a lot of time on control store and things like that. And in those days, they started to have get this, 32 by 8 ROMs on a chip, right? So one chip, you could get 32 bytes of ROM. But in reality, what is a ROM, a 32 by 8 ROM, other than an arbitrary 8 functions of 5 variables? So you look at all the control structure, and I said, I'm a Neanderthal or troglodyte, or whatever you want to call it. But here's all this control structure. Yes, we could build this overhead of a microprocessor with a PC and control store and execution, or we can just brute force, here's all the control logic. How many functions of 5 variables is that? And so we came up with something I called hybrid microprogramming, because I wanted to use the word microprogram. It really didn't have anything to do with, but it satisfied the people that wanted to be microprogrammed. And so if you look at the Nova 2, there's a crap load of those huge 32 byte ROMs on there. So most of the logic, and they were pretty fast. I forget now. I mean, it could have been a whopping like 16 nanoseconds or something.
Yeah, I think
That fast, through one of those. So you can get an arbitrary, 8 functions of 5 variables is really what you get in a ROM. It's like what FPGAs. Any people know FPGAs nowadays? Yeah, FPGA, that's what I do. That's my thing now. I love FPGAs, love VHDL, and those, use what's called a LUT, which means lookup table, right? Yeah, well, because it's RAM, because it's programmable. But that's the whole notion. Is now the ones I'm using now, I'm using Xilinx UltraScale Plus, which has 8 input LUTs. So it doesn't matter. See, in the old days, you wanted to get away from exclusive ORs or, functions with a lot of minterms, because it's more propagation delay, right? And so you try to optimize your logic to have, the minimum number of minterms. But when you have ROMs or lookup tables, it can be the most complicated function you want. It's just a lookup table, right? I mean, and that's what the Nova 2 was. Now, one of the things, the first time I ever met the founder of Data General, he comes bursting in the lab and he goes, "What's this? You guys got a Unibus?" And I said, "No," because Ed DeCastro formed Data General because he designed the PDP-8. And he had a bake-off with Gordon Bell for the 16-bit machine. PDP-8 is a 12-bit machine. And so he came up with a 16-bit PDP-8 and presented it. And Gordon Bell came up with the PDP-11. And PDP-11 was a lot more complicated. Next time you're at the Computer History Museum, they have them side by side. They got an original Nova and original PDP-11. One is like this big, and one's that big. One's X dollars, the other is X over $2. You know which one. And that's what Ed was about. He was a hardware guy's hardware guy. And he designed the Nova. Basically, the Nova architecture is, there weren't as many lawyers in those days, right? So DEC never sued him. He went off and formed Data General and let, Gordon Bell do the PDP-11, right? So, but that was basically it. He comes in. So we did get rid of this, like, gross. There was nothing you would call a memory bus. It was like sense wires and inhibit wires and stuff coming out of the processor and going to the memory core memories. There was no clean architecture. So we came up with a memory bus. And so he thought we were copying the Unibus, and he hated the Unibus. So he said, "What are you doing? What are you doing?" And I said, "Well, Ed," and I appealed to him as a optimizing hardware guy. I go, "Look at how many gates we saved. Look at the drivers. This is great." And he said, okay. And that was it. So, but the Nova 2 was my first introduction to the fact that digital isn't. What I mean by digital isn't is that everything is analog, okay? And if you've got a 50-foot I/O bus and you're driving, 64 MA, and all of a sudden all the ones, actually we used inverted logic because there are more zeros than ones, so, you know, a high was just a pull up, a low was consuming power. So when you went from all ones or all highs, which was all zeros, to all ones, and you looked on a oscilloscope on it, so if you open up that nova, don't do it around me, you know, get a barf bag out. The number of red wires that we had to put in to put in new bus drivers. So, and we put spares on the top of the board. So if you look at the Nova 2 board, you know, it's got the spare chips at the top, furthest away from the backplane, have these special quad drivers that could actually drive 64 MA and not have ground bounce that would, you know, kill your mother. Then it's got twisted pair on that. It's the ugliest board. I mean, I'm embarrassed. My only, you know, fallback is I designed it when I was 19, and I had no idea that digital isn't. Okay.
So how does a machine get from being a junior project to being a general product?
No, we were hired at Data General.
So they were confident you would deliver a product?
We would go to South Pro and work, and so we were employees at Data General. Again.
Yeah, but I mean, didn't they have a backup plan? I mean,
they had no backup plan. I mean, their thing was, okay, Larry Seligman designed the 1200, and you know Ron Gruner was the guru that designed the 800. He's off designing the Eclipse,
okay.
and that's going to be a 2-board design, and it's going to run in 300 nanoseconds. All of it is going to use. It had this new stuff called Schottky. You know, it's just fast, and you know Ron knew it, and he did know what he was doing. And it was an expanded instruction set too. It had things like multiply, divide built in. I mean, but so Larry was kind of in conflict or rivalry with Ron, and so Ron was off doing the Eclipse, and after the 800. And Larry had just done the 1200, and he wanted to know what's next. He's the one. So when Professor Tung was showing Larry around, because Larry got a Nova, because like I told you, we were juniors. We couldn't use the 70K drum. We had to use the Nova that was there. And Larry Seligman was Professor Tung's student who went off to work there. So he was given a tour and wanted to know, okay, I donated a Nova, is it being used? And he brings them by, and Dave and I are in the lab. Chances are we were there in the lab any time of day with that Nova. And, you know, we were telling him how we love the Nova and all this. And so Larry comes and says, oh, you want a job? And I said, oh, now that's when I had to think, 8 picoseconds. Do I want to stay in Cambridge with my girlfriend or go do toilet paper in Vermont? But anyways, so we get there, and we were just hired as summer interns.
Yeah, but that's what I mean. You normally don't hire a summer intern to make a product.
No, but that's what I'm telling you about little companies.
Okay.
So
How
here's
big was
Larry
the company?
Seligman is responsible for the next processor because he did the 1200.
But how big was the company at that time?
Oh, I was number like 891, so it was reasonably big. I don't know. I mean, Dave was 890. He always got it was alphabetical. That's why he was 16 and I was 17 at Rational. But he was 890, I was 891. I remember that well. And so it was a relatively big company. It already had the Nova, the Supernova, the Supernova Ed did. So Ed did the Nova and the Supernova. And then so Larry wanted to know what to do. So he said, well, you know, at first we were hired to do, we had this idea we could do multiprocessing and do a coprocessor that would do comp.
Yeah.
That was originally what we proposed as a project. But when he said, well, this is a coprocessor, we can use this, Larry goes, well, why don't we just make it a processor? And so it just evolved into being the Nova 2. And, you know, I mean, it's a small company, and you know, that's why I've never in my life work for a big company, and well, at this point, never will. I mean, right,
When was that, the Nova 2? When did you start?
72.
72, yeah.
Yeah, because it was, you know, we graduated. I have to look here. Okay, I graduated in 73, right?
Yeah.
No, I remember that. But yeah, so. And remember, I mean, there was 256-bit memory chips came out around 75 or something. I mean, you know, but the Nova 2, at that point, they had those fancy machines that we had 16K on one, you know, and that's words. So it's 256K bits on one memory board, right?
That's why I want to see that sewing machine.
Yeah, I mean, again, that's fine mechanics. That's her job. Right? But
No, but I've never been able to find any documentation on the web about them. Nobody has taken a picture of one apparently.
I don't know. I read something about Forrester, Jay Forrester,
Yeah,
who invented core memory,
yeah.
and it got into more of the manufacturing. I don't know how far, but there's ways. The internet's an amazing thing. I mean, if I were interested, I'd look into it. It's your job. You're interested, but you need to get your rational emulator working. Any other questions?
If I may go back to the rational, how successful commercially was the rational machines?
So, I mean, it was successful enough that the company got sold to IBM for $5 billion or something like that.
Okay.
But again, as engineers, I mean, I think I only got a measly $1 million out of it all. I mean, but, you know, so it wasn't like a huge, you know, a huge success. But we sold a lot because, and a lot was because of Europe. We ended up selling a lot to Scandinavia. We had a branch in Uppsala, Sweden, and you know we had Pierre. I mean, people in Europe. We sold a lot to Europe because of the aerospace industry. We sold to the FCC, the FDA, I mean, not the FDA though, the FAA. They really, the new air traffic, the whole Canadian air traffic system was all that. I know one of my first field trips was a machine failed at IBM Gaithersburg, and I had to go there, and they, of course, it was in a secure site, so we didn't have remote diagnostics. So I had one of everything, and I go in there, and it's my first experience with like, you follow this Marine with the M16, and don't look to the left, don't look to the right, just follow him, and I go there, I find out it's an FIU. So I replaced the FIU. I said, okay, I'll take this board back and we'll fix it. And they, oh, no, you can't take it out. This is a secure site. I say, well, why not? He says, you've got non-volatile memory. I'm going, we have a 64-byte non-volatile memory to hold the serial number, the data manufacturer, and the ECO history of this board. And I guarantee you that we cannot encode your whole GPS project. And the guy goes, how do you know we're working on GPS? Everybody knows you're working on GPS. So it's like they were working on something called Advanced Tactical Fighter. Had another one. That turned out to be the F-117 Stealth. But we all knew. It's even back to when I was at MIT grad school, Marvin Minsky went to Georgia, Russia, to a SETI conference. And he comes back and was telling us all about our Milstar satellites. You know, you could see the type of brand that the guard at the Kremlin is smoking, you know, and so we're all there. The next week, all these guys in black show up at the MIT lab and start saying, how do you find out about this? How do you find out about this? Marvin told us, don't worry, tell them we found out from the Russians. Who do you want to keep it from, right? He went to a conference, you know, yeah, it's a military secret, but we found it out from the Russians, so big deal. Sue us, you know, here's my handcuffs and all, right. But it's amazing how they try to keep secrets that are irrelevant, really, everybody knows.
Another
Anyone?
question,
What's
how did you price the systems?
How did I what?
Price.
Okay, the first one was $1 million.
Yeah.
And that's Arthur Rock priced it. He said Millstar. It was actually, that was Millstar, you know, the satellite system too that Lockheed was doing. And they had infinite government money,
So,
charge $1 million. And so eventually, you know, they wanted to get more penetration, so it went down. I don't know how much that was. I think that was probably only $250,000 or less. I don't know how much we charged for that. I mean, again, remember, there's these guys called sales that are necessary evil.
I mean,
They worry about prices.
That's right, that's right.
Yeah, I worried about how much it costs
Yeah.
to build, but that, you know, in those days I learned real early about margins, and they tried to have at least 4-to-1 margins. So if it costs us, you know, 50,000 to build, then they'll charge 200,000 to sell, and then they make good gross margins.
I think one of the binders we have your signature on a $50 ECO.
How much? Oh, my signature's on an
On
ECO.
a $50 ECO.
A $50 ECO. Okay. But do you know how much it costs? I don't.
No, no. I don't know.
That's the salespeople. I don't deal with that. You know, I don't know how much. Although I do remember the first one they got, it was $1 million, but right, and I know that by definition the other ones are lower, but I don't know how much. But we were reasonably successful. I mean, you know, but it wasn't, you know, because of the hardware. It was really because of the software, right? I mean, that's what Rational really was. It was Grady Booch and the Rational environment and all of that that made us successful.
And what did IBM get out of it?
What's that?
What did IBM get out of it?
IBM still owns it. They sold
still own it.
Rational Rose and you know
I think
products.
the
Rational
environment's still
Eclipse.
The environment is still.
You can go on IBM site and get Rational Eclipse. I think there's another product called Eclipse. I think it is
Okay.
based on Rational Eclipse, so programming environment for I know C++ and C and stuff. But I don't think they got a heck of a lot. But sorry, Grady, if he's going to see the tape, what they got was Grady Booch.
Yeah.
All right, okay. So IBM got a lot out of Rational, right?
So at one point, Rational quits hardware. Is that before or after IBM?
Before.
That's before.
In fact, because I left, okay, so we were designing a chip-based R1000. In fact, Dave Bernstein and I went to France to visit this IC fab house. They had this ASIC development tool, and we were pretty serious into designing a chip-based one. But finally, I remember Mike Devlin sitting down with me and saying, you know, we're just going to have to cancel this. It doesn't make sense. Because at that point, you've got the IBM RS6000, the DEC, I forgot what their number was. They started to have RISC machines. So in the early days, they did some graphs, and they were talking about multiprocessing, and they would show where it broke down, you know, like, so an MV1000, you know, you have this axis is number of tasks, this axis is execution speed. And so MV8000 was like that. You know, VAX was like that. Rational Machine was just flat. It multiprocessed like a multitask like it was going on. And that was very important. But after a while, no matter how much you're flat like that, if you're 5 megahertz, you know, at that point, you know, in the early days, 5 megahertz was fast. In those days, you were getting, you know, approaching 100 megahertz. It really wasn't, I mean, I'm talking again, mid 90s, right? I left Rational in 95. So I was there for 13 years, and, you know, most people, when I tried to, I took a year or two off, but the people, though, would look at it and they say, well, nobody in Silicon Valley stays at the same company 13 years. You must not be any good. I go, okay, that's what you think. But, you know, eventually, luckily, Intuitive Surgical decided I was good. And I switched from computer design to medical design. And, you know, I've been doing that ever since. I'm doing ultrasound right now. And ultrasound's better because we couldn't grow a third arm on the surgeon, and we couldn't speed up the speed of light. So chips caught up with a human being because the intuitive surgical robot is a Waldo. A Waldo is a class of robots that just follows the human. And that's all it does. It's not a, you do not want to use the word autonomous surgical robot in front of the FDA. The FDA,
All the patients.
if the FDA put the same constraints on a surgical resident that they put on our robot, you'd have no surgeons. You know, I've been to a lot of ORs. You stand there like this with your gloves and you touch nothing. If you're doing surgery, I don't go, hey, how you doing? But they wanted it so that somebody accidentally bumped into the surgical robot while it's doing surgery. It has to not move. Now that made it 7 times more powerful because we would have to detect, we had encoders that could detect motion, and we detect, oh, it's moving, and that's unintended motion. We have to oppose it with motors so it didn't move, right? So if it's there holding a scalpel inside your abdominal cavity and somebody bumps it, it won't slice your whatever artery. I'm not that good at anatomy, but yet it shouldn't have to be like that. I mean, people in the OR know that you don't do that type of thing. But anyhow, that's why I went into ultrasound, because that's when Moore's law caught up with digital signal processing. See, the old Accusson machines, GEI9s, things like that, it's all analog. Remember, digital isn't? But digital is now, because the FPGAs just deal with all that stuff, right? So now, with an FPGA, you get 1,300 DSPs in one little chip. You can do all this, digitize early, digitize often, right? So you go digital as soon as you can, because TI is making like 60 megasample a second, A to D converters. I mean, so you just do it all in FPGAs, and that's what I'm doing now. But 13 years at the same company didn't hurt me that badly. It's a black mark on your soul in Silicon Valley, though. So.
Do you have any idea where we should look for more machines to see if more machines have survived? Do you think somebody like Signal in Netherlands might have one in the basement?
Well, we might want to reach out to Greg Beck in Australia, and different places like that tend to be less American and throw things away, So we had a lot in Australia, and
he has one in his basement, and he says that's the only one left in that part of the country.
Right, but then Mikhail Vester, I invited him here because he lives in Uppsala, but he's in Spain right now. Well, you have another guy in Spain. It must be popular, but shake the bushes. I'm not that. One of the things is our contacts at the Computer History Museum in Silicon Valley. And I mean to go there and offer myself as a docent when I finally retire, but I'm only 70. I mean, gosh, it's not time to retire. What?
We wouldn't want a Model 100.
You do not.
We have no
I
space.
doubt you can find a Model 100.
Probably not.
I've got a I/O bay, but it's my tool set. But there must be a few out there. But and Grady might be one, but he's more interested in software than hardware. But
Why Australia? Why was that a good market? Due to
the Australian military really,
military
Adelaide. We had like 10 machines in Adelaide, and there's a guy named Greg Beck that I work with really close with. We could try to track him down.
Oh, I have his.
You have Greg Beck, yeah. So
he has a machine in his basement, but he says
he has a machine in his basement.
But he says it's lacking pieces that were sent to Terma. So then we have those.
Oh,
I think, among other things, he doesn't have an IOC.
so, but he's a contact, and there are other people. Pascal, you already know, or not?
No, I don't think.
Pascal Leroy.
I may have his email address.
And then there's Pierre.
Yeah, Pierre Lang, but we got his machine.
You got his machine, okay. Now, Mikhail, I think, would know. But, so, we had a bunch of machines in Uppsala.
Yeah,
And there's a company called Terma, I think. Or no, that was a company.
that's Denmark.
Forgot the name of the company there, though. Well, Ericsson's.
Yeah.
Ericsson had
Saab
some.
or Ericsson probably.
Yeah, but, you know, this has inspired me to be a little more interested in it. Ever since you started, you tracked me down. And I've been interested in what he's doing. I apologize I haven't had as much time.
No, don't worry.
But I've been actually doing real work as I talk.
So do I.
Yeah. Anyhow, okay, any other questions? Well, thanks a lot for the opportunity